Okay? So today, like I said, isosceles and equilateral triangles are what we're going to talk about. Let me refresh our memory here a little bit about the isosceles triangle vocabulary, right? Because there's special parts of an isosceles triangle. Okay? So first of all, let's see here. What makes an isosceles triangle isosceles? Cordell. What makes a triangle isosceles? What's like special about that? A triangle is isosceles if what is true? Don't know? All right. Sorry. All right. Let's go to then Dominic. What makes an isosceles triangle an isosceles triangle? Two equal sides. Cordell, did you hear that? Two congruent sides. Okay. So if a triangle has two congruent sides, it's an isosceles triangle. And it says right here in the definition, an isosceles triangle is a triangle with at least two congruent sides. Okay. So here, if you see with the definition, it says at least two congruent sides. So what other kind of triangles are also isosceles then? If we need an equilateral triangle would also be isosceles by this definition, right? If it's at least two congruent sides, equilateral triangles are also isosceles then, okay? So anyway, the congruent sides are called the legs. So if you look here, right, the way this picture is marked, you can see that these two sides are the congruent sides, and so those two sides are also called the legs. Well, in this case, the top angle, but its angle formed by the legs is the vertex angle. So these two legs, right, create that vertex angle, and then the other two angles that are opposite the legs, okay, are called the base angles. And then the third side is the base, okay? The non-congruent side there is the base. Okay? We're not going to do this little construction thing. I think it's a little bit much, but we're going to look here at the next page then, page 328. No, we're not going to actually do that activity. Okay, so page 328. Okay, we're going to look at this isosceles triangle theorem. Okay, and here's the key piece of information, right? If two sides of a triangle are congruent, then the two angles opposite the sides are congruent as well. All right, so that's pretty powerful, right? Two sides of a triangle are congruent, then the two angles opposite the sides are congruent. Okay, this is sometimes called the base angles theorem as well, because that talks about the base angles of the triangle. All right, so we're actually going to look at this, and we're actually going to fill in this proof here. All right, because we kind of have the skills. It basically boils down to a congruent triangles proof. All right, so we're going to start with this given piece of information that AB is congruent to AC. So AB is congruent to AC. So that's the given piece. Then we're going to say that angle A is congruent to angle A. Well, what's the reason that angle A would be congruent to angle A here? Yeah, Haley? Yeah, it's the reflexive property.
So when it's a reflexive property, it's just the same letter?
Exactly. It's something is congruent to itself, its exact self. Okay? Excuse me. Now notice here, they say that segment CA is congruent to segment BA. And you're like, well, what the heck? Where'd they get that from? Well, that's because they took this original statement here, and what they do? They flip the order, right? Which is that symmetric property, because that allows us to flip the order of symmetry. Well, flip the order of like an equation or a congruence. It's stranger they use the word equality, though, because this is not an equality statement, it's a congruence statement. But I think it's probably a typo. That should probably say of congruence, but that's okay.
Can we just write symmetric property?
That's okay too, yeah. Mm-hmm. And then here we've got triangle BAC is congruent to triangle CAB. So you see what they're trying to say here? I know it seems kind of silly, but the way they've named it is that triangle BAC, right, is going to be congruent to CAB by what? If we just said that A was congruent to itself, what type of congruence do we have within this triangle now? Kind of weird, because basically we're trying to say that the triangle is congruent to itself. But what type of triangle congruence do we have here? It's a side angle side congruence for these two. So it's the same triangle, but notice how we're naming the triangle in slightly different order. We said BAC is going to be congruent to triangle CAB.
Mr. Wood, how did they label that? Because it looks like they just said BAC and then they just went backwards.
Exactly what they did, yes. And the reason for that is they're trying to show that basically like this triangle is the same as if you took it and then also flipped it back onto itself, like that, okay? So the importance of that, though, is to show that angle B and angle C are going to be what? What can we say about angle B and angle C?
Congruent.
Yeah, they're going to be congruent. Yeah, they're going to be the same thing. That's what we're trying to show here, basically, is that because it doesn't matter if you have the triangle this way or if you flip it over and then lay it down, B and C are going to be the same angle there. So they must be congruent by CP, CTC.
So how do you know when to label it that way? Because it doesn't work like that for all the other ones.
Right, but it's because for this specific one, okay, we're just trying to show that B is congruent to C. So we're only going to just show this triangle is congruent to itself. Other triangles, you're right, it doesn't work. But for isosceles triangles...
There's only one triangle.
Yes, exactly right.
The other
That's why we
one
do it
has
that way.
two shapes.
Exactly, exactly. And we're trying to prove two different triangles are congruent. Here we're trying to show the two triangles, this single triangle is congruent to itself, basically. Okay? Now, there we've proved now that if two sides of a triangle are congruent, then the opposite angles will also be congruent. So B and C here, we now know, must be congruent. Okay? Yes?
Is all that like necessary though, because it's kind of just repeating like the same thing over and over?
So it's like, I understand, it's like almost like a very basic proof, or it's almost like, why do we even need to say this? But
A is congruent to A, you could have just been like B is congruent to B.
Right, but the reason why we said A is congruent to A, specifically for this one, is so that way we could then use side, angle, side. If we said B was congruent to B, then we would have angle, side, side. We wouldn't be able to prove the triangle is congruent necessarily to itself. I know it seems kind of like silly, but the way we're trying to do this is name the triangle in two different ways. We want to be able to say that BAC is congruent to CAB. By naming it this way, now we can see that B and C must be equal to each other, right? It shows that these two angles must be equal because they're in these corresponding positions. And that's how we get that B and C must be congruent. That's the kind of idea there. Okay? And if that still doesn't make sense to you, you're not sure why we need that, then don't worry too much about it, okay? This is just showing that we can prove this thing to be true, but what's most important here is that you just understand. In an isosceles triangle, base angles are congruent. That's what you should worry. And that's what, is more important, I guess. Okay, now, we can also go backwards from that. So here we had if two sides are congruent, then the two base angles are congruent. Okay? So if two angles of a triangle are congruent, then the two sides opposite those angles are congruent. So the reverse is true as well. If you have two congruent angles, then their opposite sides must also be congruent. So yes, you gave it.
How come that given is different than the given in the table?
That's a good question. They name them differently, but it is still the same. It's still talking about the same angle. ABC is still angle B. ACB is still angle C there. So I agree. It is different. I don't know why they do it differently like that, but
If we were to put angle B as congruent to angle
yeah,
C,
that's fine. Yep. Okay, and so then we have some sort of reflexive property here. Well, if we already have these two angles congruent, we could say that BC must be congruent to BC, right? Because BC has to be congruent to itself there.
why couldn't you do angle A as congruent to angle A?
We could, but knowing that angle A is congruent to angle A, that's going to give us angle, 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 and that's not a congruence. But I saw here that if we had BC as congruent to BC, then we would have angle, side, angle, which would be a triangle congruence, and we could use that.
Wait, so why couldn't we use angle A?
You could, but it's not going to help us, is the idea. It doesn't help us prove that this triangle is congruent to itself, basically. Okay? Angle A could be congruent to angle A, but it's not necessary for the proof. All right. Symmetric property. So we started with this, and now you'll notice that angle ABC came over here to the right, so that means the ACB is just going to switch over. Okay?
Well, how did you get that?
Symmetric property. That means we flipped the order, right? So we had this order originally, so this order flips.
Well, flips would be CBA.
The order, like the left and the right side flip is what I mean. The left and right side flip. ABC was congruent to ACB. Now the ABC is over here, so the ACB is going to go over to there.
Is that what happened in the first problem?
Yeah. Going back to the original thing, BA was congruent to CA, became CA was congruent to BA. It flipped the order. That's what symmetric property does. It flips the left-hand side and the right-hand side. Okay, I know the word flip can mean a lot of different things. Okay? So here we can now say that triangle ABC is going to be congruent to triangle ACB. Okay, and that's by the angle-side-angle congruence. And so therefore we know that AB must be congruent to AC by CPCTC. Parts are congruent. Congruent parts.
You have to put that,
Corresponding parts are congruent. For which one? I'm
the
sorry.
CPCC, whatever.
So what else would you want to put there, I guess? For the reason. Yeah, so we need to put that there because that's our reason. Once we show them that the two triangles are congruent, or the triangle and its kind of like reflection are kind of congruent there, then we want to put the CPCTC to show that they're congruent. Okay? So yes, Ekaela.
So how come that first one on step 4, like when it was being labeled BAC, and then I was like, well, let's turn it.
Ramel, I'm sorry. What are you doing right now? Okay. It doesn't look like nothing. Looks like you're standing up in front of Maddie. Show her something. I don't know. Can you have a seat, please? And like, I'm going to open your paper up. By the way, we're on page 329. Join in with the rest of class here. All right.
So
Thank you.
Remember how we said, well, that's kind of backward, and so it would be CAB. How come?
Yeah.
Like, I wrote down for number, like for the probable working
Yeah.
number 4, ABC, and then flipped is CBA. I didn't realize that we were.
A, B, C, and C, B, A.
Because that's what we did in the first problem. We just did it backwards.
Correct. Mm-hmm.
So CBA would be correct.
Yeah, that would still be correct. Yep.
Okay.
Yep. Mm-hmm. Yep. Okay. So, anyway, that's our final proof there, okay? But that's the key thing to remember then is just that the two sides in the isosceles triangle, the opposite angles of those two sides will also be congruent, and then vice versa. If you have two congruent angles, then the opposite sides will also be congruent, okay? That's the key thing to remember, okay? Equilateral and equiangular triangles also have some properties here which are kind of going to be like, duh to you, right? We already kind of talked about this. If a triangle is equilateral, then it is equiangular. If a triangle is equiangular, then it is equilateral. And we're not going to worry about, going through the proofs for that, but it's pretty obvious. It's like, well, duh, if they have equal sides, we need to have equal angles. So let me show you how we're going to use this, okay? And we're going to go to a problem like letter B here, okay? We're going to ignore all this mess down here because I don't like how they organize problems, okay? So now, looking at this triangle here, we want to find the measure of angle T. But before we can find the measure of angle T, what do we have to solve for first?
180.
X. We have to solve for X. But Jason, you're on the right track there. We want to use the fact that all the interior angles of a triangle add up to 180. So here's the thing, though. I only know two angles.
So what did you do? 3x plus.
What can I say is going to be the measure of angle S here?
1 something.
X. Zaria, how do you know that this also has to be X?
Because the other side of it.
Because the other side is X. What type of triangle do we have here, Zaria? Two congruent sides. So it's isosceles. So we're going to use that property. If we have congruent side, two congruent sides, then the opposite angles, R and S in this case, must be congruent. So X and X.
So if R was like 49 degrees, S would be 49.
You got it. Exactly right. So now we have this information. So Jason, now how can we set up our equation here?
Don't you do
3x
yeah,
plus
x
x plus x.
equals 180.
You got it. Exactly. And now we're going to solve that, Jason, what would we do?
Don't you do, well, you combine them to 3x, or all the x's.
Which would give us what?
5x.
You got it. Equals 180.
And then you divide that.
Divide both sides by 5, and we get x is, I think, 36. Thank you.
You're not finished yet.
Right, very good. You knew what question I was going to ask right off the bat, because I was going to be like, are we done? And no.
Put the 36 into the 3x.
Yeah, exactly right. Very good, Jason. You knew exactly what I was going to ask. You guys are learning. I'm glad to see that. Okay, so that gives us 108 degrees then for angle T. That's the measure of angle T. Okay. Measure of angle T is 108 degrees. Okay? Yes.
So why 180?
Because all the angles of a triangle add to 180, right? That's what we know. Remember that activity we did where we drew triangles, we tore the corners off, we put them all together to see that they all made a straight line no matter how we drew our triangle? It's true for every triangle in Euclidean geometry. Oh, I'm sorry. Sorry, Ramel. There you go. Okay? We're going to try another one here, though, so if you want to turn the page and look at the top, you can start thinking about how we're going to set that one up. Okay, so if you want to turn the page and look at the top, we're going to see it. So 332. Okay. Okay, so start thinking about how you can set up that one at the top of 332.
What's on the top of
That right there? It's a measure of angle T. Measure angle T is 108 degrees. Oh. Ooh, did I not do that? Hello? Yeah. Oh, okay, you got it. Josh, Ms. Franco would like to see you.
That doesn't mean he's in trouble.
It does not mean he's in trouble, that's right. But she would like to see you, though. Okay. So, there we go. Are we good, Ramel, to move on?
Yeah.
Okay, let's take a look at the next one. Okay, now, let's see here. Whoops, you can't see because it's like way off the screen. There you go. I don't like fractions. Okay, well, let's see. Let's check our setup here. So again, I only have two angles listed in my triangle. I want to find the measure of angle P. What could we label? What could we label angle P's measure to be, though? Okay. So, well, we don't want to just say X here. We got to be careful. So, Gabe, if you look here, right, what kind of triangle do we have? If we have two congruent sides, we call that a isosceles. Is two congruent sides. Okay. Shh. So, if it's isosceles, that means the angles opposite the congruent sides will also be congruent. So that means that angle Q is going to be congruent to angle P. So if angle Q is labeled as 3x plus 3 degrees, Gabe, what can I label angle P to be? Same thing as Q, 3x plus 3. Okay? And I guess I put parentheses around it, put a little degree symbol there.
Wouldn't it be 5x minus?
Is the R opposite a congruent side?
Well, I mean, it kind of looks all the same.
Okay, it looks the same, right? But again, we can't always just trust what the picture is. We got to trust what's the labels. Okay, the labels are what's more important. Okay, so Maddie, what's an equation I can set up here now that I have all three angles like this? What do all the angles in the triangle have to add up to? Maddie, come on. Seriously? We just talked about this. Come on, guys. This is not acceptable. Alicia, what do all the angles in the triangle add up to? 180. So we have to do, so Maddie, I'm going to come back to you now. So if all the angles have to add to 180, what's the equation we can write here? Name an angle for me. Q, what's its measure? So 3x plus 3 plus, what else? Another 3x plus 3, very good. Plus, what else? Beautiful. Must equal 180. Okay? That's the setup. That's the setup. Okay? So now we combine like terms here. 3x plus 3x is 6x plus 5x is 11x. 3 plus 3 is 6. Minus 2 is 4. Okay.
And then you do minus 4, right?
Subtract 4 from both sides.
And then,
So you get 176, and then we do get a decimal then, don't we, huh?
and then you do that, and you subtract or something. Or you find
So 176 divided by 11. Oh, it's 16. It does work out.
it. But you're not finished.
But we're not done yet, right?
You put the 6 in for P.
16 goes back in for the x for angle P there. So yeah, it's going to be 3 times 16 plus 3. Excuse me. So then we multiply. 3 times 16 is 48. 51 degrees. 51 degrees. Okay? So angle P, 51 degrees. Okay? Yes. There you go.
I got something different. They're calling you.
crikey.
They need me to take Josh's stuff up, I will.
Okay. Thanks.
I got 13.
Hello. No, she's not. Oh, great. I thought I had. I apologize. Oh, right. I got your statement. Okay. Yes. Okay, very good. Bye. All right.
Whew, I got 13.
13 for this, or for this?
That,
Right here?
yeah.
For x. Okay, so 176 divided by 11?
No, because I added 3x plus 3x plus 3x plus 5x.
Okay, you added too many 3x's together. There's 3x plus 3, 3x plus 3, and the 5x minus 2.
No, I added all the x's.
Right, so 3x plus 3x is 6x plus another 5x should give you 11x. 3 plus 3 plus 5 is 11. You might add in an additional 3 or something like that, but those don't have x's next to them. Do you see what I'm saying there, Ramel? It should only be the 3x and the 3x and the 5x
Yeah,
then.
I added 3x.
Yeah, so there you go. Okay, so there's that. Okay, this next one I'm not going to have us actually do. It does have fractions, so we're not going to worry about it. But I do want to at least show what we should be able to at least set this up, right? So it said Katie's tutorial service is going so well that she is having shirts made with the equilateral triangle emblem. She has given the t-shirt company these dimensions because she wants to, I guess, torture them, because why doesn't she just measure it? But you know, this is just a problem. That's real world. So what is the length of each side of the triangle in centimeters? So what kind of triangle are we dealing with here? Equiangular, which then also means it's equilateral. So if we wanted to set up an equation here, go ahead, Haley, tell me how we set up this equation here. Yep, it would be 3/10 y plus 9. So careful, we're not going to add these two together. If this is an equilateral triangle, what's going to be true about this side and this side? They're equal. So 3/10 y plus 9 should what? Equal 4 over 5y minus 1. And we're not going to solve that. Don't worry about it, okay, because I'm not going to give you ones and fractions like that. But that's the setup. Shh. Again, we're talking about sides here, Jason, so we just set the two sides equal. Okay, question?
Do we have homework?
So any questions, first of all, on this idea? So the two main things we talked about. If you have an isosceles triangle, if the two sides are equal, then also the two angles opposite those two sides will be equal. So base angles, another way to think about that, right, is that base angles in an isosceles triangle are equal. So the two angles opposite the two congruent sides will also be congruent. Likewise, if you have two congruent angles, the opposite sides will also be congruent. So that's the one major thing we talked about. And the other thing was, if you have an equilateral triangle, it's also equiangular. And if you have an equiangular triangle, it's also equilateral. So you can use those properties to help you set up equations. All right, Ramel, do you have a question for me? Yes, no? What's that? Okay, all right. Well, if you remember, let me know. I'll help you out, okay? So, that being said, your assignment, okay, I'd like you to work on here. I'm just going to give you a few of these to try.
So is this for homework? I'm just asking if you, like, actually
Yes, I think it will be. Okay, ooh. So we'll start at page 334. And I'm going to have you do numbers 4 through 9. And that'll be it.
it's not MS.
Doesn't that lead to
And number 19 as well. So that's his 330.
Yeah, his article is about.
Okay.
What is
I'm listening.
Yeah.